An instruction set. An instruction set is a collection of machine language instructions that a particular processor understands and executes. Now, instruction sets are basically the codes for telling the computer what to do and how to do it. When we are working with computers, they understand the binary language, zeros and ones, that's the machine language. But because we do not operate in that language, we need some human readable form of language like the HLLs we work with and the LLLs, just like the assembly language. So we code in them and the computer understands what we want and what the particular instruction is all about. Now, each computer or each processor is built on a specific instruction set that it can understand. Now, different processors, they have different instruction sets. For example, IBM has a different instruction set, Intel has a different one, and AMD has a different one as well. What I mean by the fact that processors of the same family may support instruction set of the older versions is that because an instruction set works like a base. Like, for example, we have processors nowadays, we're working with Core i7, Core i9s, etc. So the base of these processors, the Intel processors, the x86 architecture processors, is going to remain the same with addition or the support of new features, but it will never, it is very unlikely that it will stop the support of the older versions. Now, instruction format. And by instruction format, this is what comprises an instruction. It's the length of the instruction, how long the instruction is, the type of instruction, what kind of instruction is it? Is it a operation like the multiplication, addition, or does it mean to store or fetch data or fetch data from the IO, or load some kind of operand, etc. Then is the length and position of the operation codes in the instruction. Operation codes are basically what they define what kind of operation is to be performed on the instruction, and length and number of the operands. Operands are basically what the operation is performed. It can be a data or it can be a variable, anything. The major parts of an instruction. As visible from the figure given, an instruction comprises of the opcode, the addressing mode, operand, or address of the operand. Now, opcode is basically the operation code which determines what kind of operation it is. Addressing mode basically tells the system, it is very important, and it tells the system that how you're going to fetch the data. Now, we will get into the addressing modes later in the presentation. So I will just give a brief overview over here about the instruction parts. Now, operand or address of the operand basically means that where the operand is on address of the operand. Sometimes what happens is that the operands are stored in registers. So the instruction is formatted in a way that once the instruction decodes, the whole process is like, you fetch the instruction, then you decode it, and then it is executed. So once you decode the instruction, you get the address of a register where the operand is stored. So that is why it is written the address of the operand. Now, opcode and addressing opcode is basically in the form of bits. Now, those bits indicate what kind of operation it is. It's the addition, multiplication, etc. Because each operation in a computer system is given a particular bit, which indicates what the operation has to be performed when it is given that bit. Okay. Now, coming to the example. Now, if we have a 32-bit instruction, and this is how that instruction is, divided. The opcode can have like 0 to 5 bits. Then the 6 to 7 bits are for the addressing mode, and 8 to 31 bits are for the address of the operand. Now, the addressing modes, like 6 bits can perform like, 2 to the power of 6, or like, 32 operations by the combination of 6 bits. So if you have for the opcode, you have like 0 to 5, 6 bits. So 2 to the power of 6 would be 32. So these 0 to 6, 6 bits can perform 32 operations on the data. And when we talk about the addressing modes like 5 and 6 to 2, so 2 raised to power 2, that means that 4 addressing modes are possible for this machine, this particular machine that we're taking an example of, and that addressing mode basically depends upon the architecture of the machine. And in the operand case, the size of the data could be maximum 2 to power 24, like 8 to 31, so they are 24. So the data, the operand size could be maximum 16 MB. So that means that this is like this, the maximum physical memory supported by this machine is like, 16 MB. That's because of the operand size. Okay, so we have already discussed about this, that the opcode field is basically, it defines what kind of operation is it. And the operand field, it can be data or the address of the data. Now, operand addresses, now operand can not only be a register, it could be a memory address, it could be an IO address, and there are certain addresses that it could be a part of. Now, instruction set architecture. As we have seen from the starting, from the landing picture also, that it works as an interface between the hardware and software of a computer. And it is the only way that you can interact with your hardware through the processor. So instruction set is basically the only way that you can interact with the hardware of your computer. And when you command, like for example, if you have to command something, you have to speak its language. And the language of the computer, that is the instructions that we are supposed to give it. And that is all formulated in the form of instruction set architecture. Just consider is as a grammar of computer. So if you want to know the language of the computer, you need to know the grammar. Just like, for example, if you want to speak English, you need to know English grammar to speak it. You can never be fluent in a language if you don't know the grammar, you don't know the syntax, and you are not vocally capable. You don't have the vocabulary of that language, basically. If you don't have the vocabulary, so you will never be able to understand what that language, what type of words to use and how to speak that language. And basically it's now, okay, fine. So now we have taxonomy. ISAs differ based on the internal storage in a processor. Accordingly, the ISAs can be classified as follows. Now, instructional architecture can be classified into the three general organizations. This is the single accumulator organization, general register, and stack organization. Now, stack organization basically comes under the memory. It's register also, and it's the memory stack also. So let's see what this this organization is all about. Now, single accumulator organization. When we talk about single accumulator organization, we have to keep one thing in mind, that when we design a system, there are certain goals for a system, right? If you want your system to be cost effective, so you have to think of the options or the components to put in it that will be cost effective. Now, and if your goal is to make your system as fast as possible, so you will not care about the cost. Similarly, when we talk about the single accumulator organization, register is one of the fastest memories out there, but it is the most costliest as well. When we talk about single accumulator organizations, here we have an ALU, arithmetic logic unit, and we have an accumulator register, and then we have two registers, PC register and IS, program counter and instruction register. Program counter, it stores the address of the next instruction, and instruction register actually works with the instruction itself. And accumulator, basically, we can tell that accumulator performs, like functions, different functions. So accumulator is a register. It is usually of 8 or 16 bits, and all of this is connected to the memory using the common bus. And when you are supposed to make your systems cost effective, single accumulator is used because they support single address instruction. And they only use one register for the instruction. Single accumulator, as is given by the name, they use only one register for performing the instructions. Now let's come to the example. If we have an instruction, let's say x is equals to a plus b. So we are given an operation in which we have to store the value of an operation a plus b. We have to do addition of two numbers, and we have to store it in another variable. Now, what this is basically an assembly code, and what it means is that load a, that is the value of a, will be stored in the accumulator, and in that value we will add b, and that value will be stored in x accumulator. Now, in this, the number of micro operations increases. Why? Because less operands are used. We have to use less operands because we don't have registers to store them. So, number of registers are limited, and we have so the micro operations are basically increased in single accumulator organizations. Okay. Now, moving on to the next one, the journal address organization. Now, in the journal address organization, number of registers are more. So, the more speed and the cost of hardware is not an issue. In the single accumulator, we saw that if the cost is an issue, so because it is cost effective, you can go for the single accumulator. But if cost is not an issue, then if you want more registers and you want your system to be faster, then you can use the general address organization. In general address organizations, we have more registers to solve our problem at hand. But because of that, the size of the instruction increases, because obviously, when you can see from the example given of the instruction in a general address organization, we have the addressing mode, and then we have the opcode, then we have destination opcode, source opcode, source operand, and source operand. What does this mean is that we can have different operands to perform on the same data. When we see the example, then we can get more clear about it. Now, in the example, what we have is that we are supposed to perform an operation or multiplication operation, but it is like we have to store the value of a an addition operation a plus b, which will be multiplied by c plus d into x. So we can use two registers. Now we used this is again in assembly language code. We use the add is the instruction, and add is basically the operation, and r1 is a register in a and b. In first r1 register, we stored the value of a and b, and we added them with the help of this add operation. In the second part, we again added the addition. We again added c and d, and then we stored that value in the second register. And now what we did was that in the we multiplied and stored the value in the x of both of the registers. Now, with the help of this, because can you consider when if we would have to do it with the single accumulator register, we had to, store, we need to have a lot of micro operations to perform the same thing. But in the general address organization, because we have a lot of registers at our disposal, so we can use multiple registers to solve the problem. So the number of micro operations is less. The size of the number of instructions are reduced, but this length of the instruction is increased in this. So, and when the length of the instruction increases, so this is like, in the computer, or it's part of the computer organization, when the length of an instruction increases, that means the size of the database will also increase, because database needs to carry that instruction over to the memory, to and fro the memory. So when the size of the data bus also increases, number of registers also increases, so cost is also increases. So if cost is not an issue, then the general address organization is better in performance than the single accumulator organization. Now, coming to the register stack organization, what happens here? Where the operands are put into the stack and the operations are carried out on top of the stack. Now, here we consider that all the registers are in one stack, and we take the help of those registers to solve the operations on the given instructions. Now, all the registers are implemented as a stack, and this property of the stack is LIFO, last in first out. So the two basic operations in a stack are the push and pop operation. Push operation is used to insert the value, and pop is to take out the value, basically the input and output. And both RAM and the registers can be implemented as stack. Now, in an example, let us consider registers as stack, a 64-word register. Okay, so if we have a 64-word register, like 0 to 63, we have the stack of registers. We have 64 registers. So one register can store one word. 64 general set of registers were implemented as a stack of 0 to 63. Okay. So there is a stack pointer that is used, and that pointer indicates that either the stack is full or not. And it contains the address of the value to be pushed in pop. There are two flags that are full and empty, and they indicate that the stack is full or not. So if we have the zero value at the full, that means that stack is not full. And if we have one value, that means that stack is full. 0 and 1 indicate binary, so it indicates either the stack is full or not, these two flags. Now consider an example where the size of the stack pointer is 6 bits. So if we want to insert a value A and B in the register stack, we have to push we need to use the push operation, and the stack pointer needs to be iterated to store value. For example, if the stack pointer is pointing at the last address, so it will have to move up because we are going to insert the values, and as the values insert, the stack pointer will be iterated along with the values. And when we pop the values, mean that when we take out the values for any kind of operation, just like multiplication, addition, any kind of operation, so as the stack is LIFO, so the values will be coming out, one by one in the form of last in, first out. The last value to go in the stack will come out first. And zero address instruction is used in register stack. Operand address is not mentioned. Okay. Zero address instructions means that if we have an instruction, like the starting address of the instruction would be what? If we have from 0 to 63, right? So the starting address, where the stack pointer will point would be the 0 address. So these, for implementing these kind of instructions, register stack organization is helpful. So if we have a simple operation, A plus B, the same example that we saw, but without storing it in any value, we just have to perform the operation. So this is how the stack organization will perform. Like we have to push in A and push in B, and then we add them both. Then we push the operand C and D, and then we add them, and then we multiply all of this. Now, here, as we have seen earlier, we did mention some, like operand along with add, addition, and multiplication operation. But why we did not over here? Because there is address is considered as opcode, and it is a 0 instruction. So instruction size is less, and operand value is already written. So binary operation, it's the binary operation, right? So binary operation will be performed on the last two. For example, you have entered A and B into the stack. So if you add those, they will all automatically, only two operands are there, so then it will add only two of those. And if you push C and D, it will add only two of those, and then it will multiply the resultant of these two adds, and then the result will pop. Now in memory stack organization, same as register stack organization, in memory stack organization, the memory of the RAM is implemented as a stack, and CPU is directly connected with the RAM. So what we do is that this is considered as a stack, right? This stack is a memory stack. There is some space for the data operand. There is some space for the program instruction. So let's consider, for example, if we have addresses from 1000 to 4000, right? So 1000 to 2000 would be the program instruction, like scanf, printf, etc. And from the data operands, we have like consider 2 to 3000 is for the memory location, is for the data operands, and then 3 to 4000 would be implemented as a stack. And the same, and it will be operated on as in the same way as the register stack operates on. Now, register stack versus memory stack, what is basically the difference between the both? In register stack, the number of registers is more, okay? But if RAM is implemented as a stack, the cost of register is more. So basically what they mean to say is that because the register stack, in register stack, the number of registers is more, and we have to, at some point we have to keep the cost factor in the mind. So if we consider the cost of RAM and the cost of registers, so implementing more registers will be more costlier than implementing more RAM. So in most of the cases, we go with the memory stack organization. Why? Because the cost of RAM is it is a bit affordable than the registers.